Welcome to the next lecture in the series of lectures in wireless research, where we are developing few key insights in how to model the wireless communication channel. In the previous lectures, we have discussed the detail of multipath fading, which relates to delay spread and which then corresponds to coherence bandwidth. So basically, we defined how the channel behaves in frequency domain. What is the coherence bandwidth of the channel when there are multiple scatterers, reflectors and refractors in the vicinity of the transmitter and the receiver. In this lecture, we will see what happens when the transmitter and receiver is in motion, and we will develop this concept that when that motion takes place, then there is what is called a Doppler shift in frequency, and that corresponds to coherence time of the wireless communication channel. So it's very dual in nature with respect to multipath fading. There, the multipaths arrive at different time instances which give us coherence bandwidth in frequency domain. The characterization of the channel here, it's just opposite. There is a frequency shift in the channel which corresponds to the time characteristic of the wireless communication channel. So here we are looking at something which is dynamic in nature, that a mobile terminal is moving. So it is moving in this direction. So it was earlier supposed to connect from S to D, source to destination, in this path, but now it has reached here, and there are other transmitter and receiver pairs that are also moving in the same communication channel. So we can understand that whatever the signal transmission was in the first place will not remain the same, and now the signal will be sent like this. The signal will be sent like this because now the source comes from S to S1, say, and from S1 to D it will be required to be transmitted, and therefore there is a relative motion of the transmitter. Remember, we discussed that all the transmitter in wireless communication systems takes place using EM waves, and EM waves are nothing but at a speed of light we are sending signals which are characterized in wavelength and frequency. So what happens when this transmitter itself moves in a certain direction? Then the concept of Doppler shift comes. The Doppler shift is basically a shift in the carrier frequency through which the transmission was taking place. Of course, the last element of the transmitter is the antenna. The first element of the receiver is the antenna. Therefore, the transmission has been done in passband, which means after modulation. So after modulation at a high frequency, we transmit the signal at a carrier frequency of Fc. This carrier frequency suffers a shift. Why? Because of the relative motion of the various scatterers in the wireless communication system. The frequency shift that arises is said to be the Doppler frequency shift, or Doppler shift, and that is defined by this formulation: F suffix D is equal to V upon lambda into cos theta. What is lambda? Lambda is C for F, and F happens to be Fc. So we can also write as V upon C cos theta Fc. What is cos theta? So if there is a car that is moving in this direction, the user is inside this and is trying to connect to the mobile, then it makes an angle theta here. This angle is with in the direction of the propagation of a direction in which the car is moving and the direction of propagation of the signal. So this is theta. So here we define how can we mathematically compute what is said to be the Doppler frequency of the communication system. Now, this Doppler frequency is a relative concept, and by relative it means the frequency will reduce when we are moving away from the receiver, and the frequency will appear to be larger when we move towards this receiver. which means to say that if we are moving away from the receiver, we will experience a frequency which is smaller. When we are moving towards the receiver, we will experience a frequency which is larger than the carrier frequency, which means when you are away, you will experience a frequency which is less than the carrier frequency. And by how much? By the Doppler frequency. Similarly, in the case where it is towards the receiver, then it will be Fc plus Fd, which means it will be increased. So it is a relative, and it will be basically Fc plus minus Fd depending on whether it is coming towards or it is moving away from the receiver. Now this is frequency change that is applicable due to motion of the transmitter or the receiver or both in a wireless communication system. However, since there is a change in frequency, it will obviously affect the time dispersive nature of the channel. So as we defined the coherence bandwidth, B suffix C, as the bandwidth in which the range of frequency in which the communication system considers the signals to be correlated, there is also a concept of coherence time. So the time varying wireless communication channel is characterized using coherence time. This time variation is because of this Doppler shift. The channel changes due to the motion of various objects in the signal. Therefore, what changes? This motion manifests in frequency domain as Fd. Now this Fd has a maximum value because the cos theta can be at max plus minus 1. So the Fd max is V upon C Fc. Remember, there is a cos theta also in Fd. So we define something which is called maximum Doppler shift. This maximum Doppler spread is basically reciprocal to the coherence time of the channel. What is the coherence time? It's the duration in time in which the channel behaves properly in a layman language, which means it does not change rapidly in that time domain, and this time domain will be defined by the maximum Doppler spread, and the maximum Doppler spread is in turn related to the various objects that are moving in the communication channel. So therefore this Tc is basically 1 upon Fd max, where Fd max is the maximum Doppler shift. So this is our coherence time of a channel. This is directly related to the motion of the various objects in the wireless communication system. If everything is stationary, Fd is 0, the coherence times is infinity, which means the channel behaves normally, it behaves uniformly over a very large span of time, and ideally infinity. But whenever there is a relative motion, there will be some Doppler spread Fd. Therefore, there will be some Doppler shift max Fd max, and its reciprocal will give us the coherence time of the communication channel, the duration in which the channel behaves similar to the signals. How it is related to the signal? Now assume that there is a signal that has a bandwidth FM, which is that the signal is band limited in frequency domain to FM hertz. Then what is the time period? Basically it's reciprocal. So the time period of the signal now is Tm. We are now going similar to what we discussed to the coherence bandwidth. This time it is about the coherence time of the wireless communication channel. If Tm is the time period of the signal that is being sent through the communication channel that is experiencing a coherence time Tc, then there can be these scenarios. The first scenario is that when this signal's time period is smaller than the coherence time, which means the channel is behaving similar in the complete duration of the signal, then the channel remains invariant. You can see from this diagram, this is the channel impulse response, suppose versus T. It's a very rough demonstration of the concept. In this case, we are tackling that Tm is less than Tc. So this is Tc basically, And suppose that there is a signal that has a Tm, and we are assuming that this Tm is smaller than Tc, then you can understand whatever the variation in the channel it is there, it is going to be, there will be variations. It's not as if it is going to be constant, but whatever variation are there, they will be recorded more coherently, which means they will behave more in a similar fashion every time you record the channel impulse response when the signal's time period is smaller than the coherence time. So this kind of fading is said to be what is termed as slow fading. The slow fading is a concept in which the channel coherence time is larger than the time period of the signal that is being sent through the communication channel. The second case is when the time period of the signal becomes larger than Tc. So you can visualize, just for visualizing purpose, the same channel, the impulse response of the same channel. So it is having a coherence time of Tc till which it behaves normally. In this span it behaves normally, then more abruption will be there. And the signal is having a time period which is very large compared to Tc. So what will happen? During one complete cycle of the signal, the channel itself changes, and it will change various times, and therefore the channel changes during the transmission of the baseband message signal, and this is termed as what is said to be the fast fading phenomenon. So slow fading happens when the time period of the signal is smaller than the coherence bandwidth, vice versa. When the time period of the signal becomes larger than the coherence time of the signal, the channel changes multiple times, leading to what is said to be the fast fading of the wireless communication system. This can be compared to the concept of coherence bandwidth that we discussed in the last lecture, the link of which is given in the description. Thank you for watching this lecture. If it helped you in any case, in any way, please like and subscribe so that we are motivated enough. And for any research assistance or collaboration, you can contact us directly. Thank you.